All right, in this lesson, we're going to be actually talking about states of matter and really changing states. Now, this is all also within the Discovery Ed Tech book. I'll link that on the calendar date as well, but I'm going to just roll through our notes. You should have these in OneNote as well. And so, again, just a little bit of a recap of what we've drawn out before, but here's a more professional appearance of it. Our states of matter, we have really are three more common ones are solid, liquid, and gases. They're the more familiar ones. Now, there is another one that I would love to show and talk to you about later, and that is plasma. And that is actually a fourth state of matter that we'll talk about. However, solids, liquids, and gases are the most familiar ones. Now they get that state because of the motion and the arrangement of the particles. And the particles, again, this is a very important thing. The particles are always moving, even in solids, right? Even in solids, even in solids. So let's talk about solids. Solids have a definite shape and a definite volume. They don't slide by each other. They simply vibrate in place and they are very close together. So picture a dice inside of a Erlenmeyer flask, and that's what this picture is. If I put a dice inside that, well, it wouldn't change. It wouldn't melt in like goo or whatever. It would stay solid. However, know that inside that solid, the particles are always moving. They're vibrating. However, if we now look at liquids, right? Liquids, if we were to pour a liquid in that same flask, they're going to take the shape of it, right? And so they have a definite volume. There's a certain amount of it, but no definite shape. They take the shape all the way down to the bottom corners of the shape they're in. Particles slide by each other. However, the forces of those particles keep them together and they take the shape of the container. Now, gases, on the other hand, gases have no definite volume and no definite shape. They're in here just shooting and flying all around in every which direction, bouncing off the walls, flying by each other, right? So particles are far apart from each other and they fill the space to fill it completely. Particles affect each other when they collide and they can squeeze into smaller space. Picture a bike pump. You can take air from outside, you know, the outside and pump it into a bike tire. You're compressing that air into a smaller space. Or picture a balloon. Same thing. Now, particles spread out evenly. So if we were to kind of visually look at this and identify, well, which one is which? Well, I have, let's call this first one A, let's call this one B, and this one here C. So a solid, again, would be like our snowflakes, our ice crystals. So this would be a solid. And if we look at this next one, this is kind of like a beaker or a flask of some sort, but it's really a beaker here. These are sliding by each other, and there's a little bit of space that allows these to kind of navigate and slide by. So this would be C, a liquid. And then we have our third one here, process of elimination. And what we're really looking at, guys, is this steam that's coming off of the pot, right? That steam is what then is making this a gas, right? And the gas particles, again, they're flying boom, boom, right? They're, ricocheting off the walls, they're flying by each other and moving very sporadically. So that is a gas. Now, when matter changes state, the total number of particles in that matter, they stay the same, right? We aren't changing H2O, the same number of particles in an ice cube. When it melts, we have the same number of them when it turns to a liquid. So how is melting different than freezing? Well, we might classify matter by its color or texture, right? But another way we classify it is based on its state that it's in, what state it is in. Now, obviously, we are here in Indiana, but we're talking about matter as in solids, liquids, and gases, right? So changes in state are also called phase changes. Now, a phase that is in, because remember, things can change, right? We can turn solids into liquids. We can turn any solid into a liquid, right? Well, not every solid, because we'll do a little bit of a demonstration with dry ice, right? Hint, hint, nudge, nudge, something to come your way. But we can even take like iron and metals and melt them down and turn them into liquids. Now, this is also why we have what are physical changes. Physical changes are when you change one state to another. Now, one way we do that, and I just mentioned it before, is melting, right? Melting is when you turn a solid to a liquid. And this occurs when energy, usually it's hot, depends on the melting state or melting temperature of an element. But we have is added. So when I add energy, usually heat. Oh, usually heat is added. Then those particles gain energy. They start moving around faster and faster, and then they melt. They turn to a liquid. Right now, particles, when heated, gain energy and move faster. Eventually, they slide past one another, and it flows like a liquid. Right? Now, the opposite, well, and I will say that this is a big deal. Particles heated gain energy and move faster. This is a big deal. I'm going to just hint, hint, nudge, nudge. You'll want to know this, right? Now, the opposite of this is freezing. Now, freezing is when we turn a liquid to a solid, right? So it occurs when energy is lost. If you know one, then you'll do the opposite and you get the other. So if I know melting is when energy is added, freezing is when energy is lost. Particles lose energy and they slow down, right? And they slow down so much that then they turn into a solid. However, remember, those particles never stop moving. The freezing point and the melting point are the same, right? This is a big deal, right? Water freezes at 32 degrees, but at 32 degrees, ice will then melt. It all depends on what trend the temperature is continuing to go, which is why at 32 degrees, if the air temperature and the ground temperature are 32 degrees, we get that weird freezing rain, that slushiness, right? And so it all depends on what direction the temperature continues to, if it freezes or if it melts. Now, each material has its own melting point. I just talked about water. H2O is 32 degrees Fahrenheit or 0 degrees Celsius. That boiling point of water is 212 degrees Fahrenheit or 100 degrees Celsius. Now, let's now talk about the gas part of this, right? And so evaporation and boiling are different from condensing, right? So if we have vaporization, right? Vaporization has that vapor, right? Water vapor, and that is what is in the air that we have. So vaporization is a change from a liquid to a gas, and it occurs in two ways. One is boiling, and the other is evaporation. Now, if it rains, we have puddles outside, but it doesn't mean that we boil them away. They just evaporate. So boiling is when bubbles of water rise to the surface of the water. So when you put a pot of water on a stove, and I'll show you in a demonstration video here later on of water boiling, it gains energy, turns into a bubble, and then it gets to the surface and pop, right? And that water vapor then goes into the air. It evaporates. However, the slower version of this is evaporation, and that is when it's a slower process when water molecules on the surface first gain energy and then they vaporize. The ones right at the surface, not down low in the puddle, right? Now, the opposite of this would be then condensing. Now, condensing is when we take a gas and turn it to a liquid, right? So a gas particle, when gas particles cool down and they lose energy, they turn from a gas to a liquid, right? They condense. So water vapor molecules come in contact with a cooler surface they lose heat. So picture an example of if you were to, right? Hopefully, if you put your hand to your mouth and you breathe out big and slow, you feel that heat. Well, if you did that to a cold window in a car in the winter, you would get that fog or that condensation on the window. Or if you had a hot shower or a sink and that hot air is then touching the cool glass, it's going to condense. It's going to create that fogginess on the glass. Or if you had morning dew, not mountain dew, morning dew outside in the summer, when the hot air touches the cool grass blades, it condenses and you get that wetness on the grass blade. That's condensation. And then temperature and state, well, in order for matter to go through condensation, its temperature must initially decrease. And in order for matter to go through boiling, the temperature must initially increase, right? If we're going to boil, that temperature has to go up. If we're going to condense, that temperature must then come down, right? And then when the temperature of a liquid is raised high enough, it eventually becomes a gas, right? Now, ice changes to a liquid when it gains energy, right? It's heated, right? Those particles gain energy, they move around, they start sliding by each other. Now, if we change a state, it will not change the amount of matter in a sample of the substance. And we actually call this conservation. We conserve conservation of mass, right? And this is a big deal, right? The matter cannot be created nor destroyed in a closed system. So some things will appear that they disappear, right? So if you were to, maybe your parents, maybe you, I don't know, maybe you drink tea, right? So let's put a nice little teacup here, right? We'll put a little saucer out, and it's got its little handle here, right? Beautiful teacup, right? Now, if I were to say, well, I've got 100 grams, if I were to actually put that on a scale and I had 100 grams with the teacup in there, right? But then if I were to add a sugar cube, right? Because some people have sugar with their tea, right? And so if I were to plop that sugar cube in the tea and that sugar cube was 5 grams, that means in total, I have not lost. That sugar is going to dissolve in that tea, but in total, it's going to have 105 grams as a total mass. I haven't lost the sugar, it's just dissolved in that liquid there, right? So your notes should look somewhat similar to mine. I have pushed this out to yours in OneNote, but again, let me know if you have any questions. This is all about changing states of matter.